Okay, so in this video, we are going to talk about polarity. We're not going to talk about polar bears, even though they are super cute, but we are going to talk about polarity, and we're going to talk about how the electrons are shifted or not shifted in a molecule. Really super important, especially for those of you going on to 1211. The polarity of a molecule plays a huge role and really dictates the behavior of that molecule. And definitely in terms of medicine, you are going to see that polarity plays a huge role in how different biological molecules behave in the body and how pharmaceuticals behave in the body, whether they are polar and dissolve in water or nonpolar and dissolve in fats, whether or not they cross the blood-brain barrier. So really crucial that you're able to understand whether a molecule is polar or nonpolar and why. All right, so the first thing to understand in our conversation about polarity is this term called electronegativity. And chemists love to shorten things, so you are going to see electronegativity written as capital E, capital N. And this is the ability of an atom to attract electrons to itself. We're not talking about these atoms actually removing or taking an electron away from another atom. We're actually talking about the ability of that atom to pull bonded electrons towards itself. And so what you're going to see, and you will be provided this information, you'll be given a chart, and on that chart we will show you what the relative electronegativity is. So here you can see, and they're denoted by the numbers underneath the symbol, that fluorine here is the most electronegative element on the periodic table. It has an electronegativity of 4.0, whereas francium down here at the bottom has an electronegativity of 0.7. That is the least electronegative element on the periodic table. What this means is that fluorine is going to do a better job of pulling or attracting electrons to itself than any other element on the periodic table. So the higher the number, the greater the atom's ability to attract those electrons to itself. Okay, so what this electronegativity is going to allow us to do is to talk about different types of bonds. Now, we've already talked about covalent bonds, and we've defined those as bonds between nonmetals where our electrons are being shared between two elements or two nonmetals. And ionic bonds are going to be between metals and nonmetals. And there you have a transfer of electrons or an attraction between a positive ion and a negative ion. So what we're going to focus on here is how we are going to use that electronegativity to specifically define what kind of covalent bond we have. So we have two different types of covalent bonds. We have a nonpolar covalent bond, which is an equal sharing of electrons, and a polar covalent bond, which is an unequal sharing of electrons. Now, to help us figure out what type of bond this is, we're going to look at the electronegativity, and we're going to take the difference in the electronegativity. And so that arrow, right, or not that arrow, but that triangle, that stands for difference. And so we're going to take the difference in the electronegativities of the elements that are in that particular bond. So if the difference is between 0 and 0.4, it is considered an equal sharing of electrons. So I'm going to give you an example, couple of examples. So hydrogen bonded to hydrogen. Both hydrogens have an electronegativity of 2.1. And so if I take the difference in the electronegativity here, and you probably don't even need me to write it out, 2.1 minus 2.1 is 0. And so I'm going to have an equal sharing of electrons there. If I were to take a look at the bond between carbon and hydrogen, carbon has an electronegativity of 2.5, and hydrogen has an electronegativity of 2.1. So that's terrible. Triangle. Let's try that again. take that difference in electronegativity and take 2.5 minus 2.1. And I always recommend you take the larger number minus the smaller number. You get a difference of 0.4. So that is going to make that a nonpolar bond. It is between 0 and 0.4. For a polar covalent bond, your difference is going to be between 0.5 and 1.9. So an example of this would be the bonding between hydrogen and chlorine. And again, hydrogen's 2.1, chlorine is 3.0. And my difference in electronegativity here, again, take the larger number minus the smaller one. 3.0 minus 2.1 gives me a difference of 0.9, which falls in that range between 0.5 and 1.9, which means that your electrons are not equally shared. And we'll talk about in the next slide exactly where those electrons hang out if they're not being equally shared. All right, last example is our ionic bond. I'll do my favorite example here, sodium and chlorine. Sodium has an electronegativity of 0.9. Chlorine, let's do that in a different color, shall we? So it's a little easier to see. So sodium is 0.9 and chlorine is 3.0. And so if I take the difference in that electronegativity here, that's 3.0 minus 0.9 gives me a difference of 2.1. That's greater than 1.9, so that tells me that I'm dealing with an ionic bond. So that's how you would go about using that electronegativity table to help you figure out whether a specific bond is a polar bond, nonpolar bond, or potentially ionic bond. All right, so let's dive a little deeper into what's going on in these bonds. So let's start by talking about the polar bonds and talk about exactly what that looks like. So in a polar bond, you've got an unequal sharing of these bonded electrons, and it has something called a permanent dipole moment. So let's talk about exactly what we mean by that. So we did the bonding between hydrogen and chlorine in the previous slide, right? And so we said that it is definitely a polar bond. And I'm just going to go ahead and remind you by writing out the electronegativities here below each element. Okay, so it's definitely a polar bond, right? The difference in electronegativity here is 0.9. Now the electrons are always going to be shifted towards the more electronegative element. Always, write that down. The electrons are always going to be shifted towards the more electronegative element, which means that this molecule or this bond is going to have a permanent dipole moment. Now the way we are going to represent this dipole moment is to draw an arrow above the bond. The arrow always points towards a more electronegative element, so in this case it's going to point towards chlorine. And then by convention we put this little plus sign here, which indicates that the electrons are shifted away from hydrogen. So literally the electrons are shifting away from hydrogen and towards chlorine. But remember, this is still a covalent bond, so those electrons are still being shared between the hydrogen and the chlorine. They're just shifted, right? They're not being equally shared. So it has a permanent dipole moment. Now we can also talk about this dipole moment or use a different notation to show how the electrons are being shifted. And to do that, we can draw what's called a lowercase delta. So it looks like an 8 that you didn't quite finish. So negative lowercase delta on the more electronegative atom, and a lowercase delta positive on the more slightly positive, or the atom that the electrons are shifting away from. And what this indicates to us is a partial charge. Okay, so this is a permanent dipole. Means that the electrons are permanently shifted away from hydrogen and towards chlorine. What that's going to do is it's going to make the hydrogen slightly positive and the chlorine slightly negative. This will become very important a little bit later when we talk about whether the molecule itself is polar or nonpolar. With a nonpolar covalent bond, again, you've got an equal sharing of those bonded electrons. These bonds are not going to have a permanent dipole moment, but they're going to have something called an instantaneous dipole moment. So what happens here is that the electrons are never simply static. They're never just kind of hanging out and sitting between two atoms. They're in constant motion. And so at any given moment, those electrons in the bond may instantaneously shift towards one atom or the other, making it an instantaneous dipole and making it so that one atom is slightly positive and one atom is slightly negative. But again, it's instantaneous. It does not last. Now, all of the diatomic elements are going to form nonpolar bonds since they are bonded to each other. So, for example, right, we know our diatomic elements are, and Brinkelhoff would be the way I would go about remembering that. Brinkel, well, that would be I next. Brinkelhoff. Okay, so all of those, and those are all, I should probably put commas in here so that you can see they are all of our diatomic elements. They are going to be bonded to each other. They're actually extremely reactive and can be dangerous when they're a single atom. And so they do, in nature, bond to each other. It makes them a bit more stable. But just be aware that all of your diatomic elements, your Brinkelhoffs, are all going to form nonpolar bonds. Okay, so since we have talked about electronegativity and bond polarity, we're going to take this together and talk about molecular polarity. So we're going to talk about whether or not the molecule as a whole is polar or nonpolar. So there are going to be a couple of different things that we're going to need to consider when we're thinking about whether this molecule is polar or nonpolar, which is why it's really important for you to be able to do Lewis structures, to be able to understand your geometry, and then be able to determine whether or not the bonds are polar or nonpolar. So the first one we're going to talk about is a nonpolar or nonpolar molecules. And in order for a molecule to overall be nonpolar, you have to have nonpolar bonds only, and or those dipoles have to cancel out, so you have no net dipole. And really what I want you to be thinking about is symmetrical. If that molecule is symmetrical, it is going to be nonpolar. So I have two examples for you. And let's do this first one, right? So I have CH4. And if you remember in the previous slide, we talked about this bond, right? We talked about the carbon-hydrogen bond. And we said that carbon has an electronegativity of 2.5. Hydrogen has an electronegativity of 2.4, and so therefore the difference in my electronegativity here is 0.4. There are no polar bonds in this molecule, so it is going to be nonpolar. The next example is carbon dioxide, and here is the structure for carbon dioxide. Okay. Now, if I talk about the electronegativity here, carbon has an electronegativity of 3.5. Carbon is 2.5. Right? And so oxygen 3.5. So what I have here is I have a polar bond, or I have two polar bonds in this molecule. And so for each of those bonds, I have a dipole moment. But those dipole moments are the same. And I always use the visual of, say my kids are older now, right? They're 24 and 21. But when they were younger, right, I might have my son trying to get me to go in one direction and my daughter trying to get me to go in the equal opposite direction. And so if they're both pulling on me in equal opposite directions, we're not going anywhere, right? There's no overall net pull. It's the same thing here. So because those pulls, those dipoles are pointing in opposite directions and they're the same size, they cancel out. And really what I'm looking at here is this molecule has symmetry. It is symmetrical. So that is going to make it nonpolar. So nonpolar bonds and symmetrical tell you that your molecule is nonpolar. Now for your molecule to be polar, you must have a polar bond. And those dipoles cannot cancel out. And so what I want you to be thinking of for a polar molecule is it is asymmetrical. And then the other really important thing here is that if, oh, that's not what I wanted to do. If you have lone pairs on that central atom, your molecule will always be polar. All right, so let's take a look at water as our example here. Okay, put my lone pairs on here. Okay, so I know that hydrogen has an electronegativity of 0.1. Oxygen has an electronegativity of 3.5. And so what I have here is I have definitive, right, definitive polar bonds. And I drew out water this way specifically. So if you remember from a previous video, we talked about water, and water is a bent molecule. It is not going to have symmetry. So those dipoles are not going to cancel out. The other thing that I want you to focus on here and think about is the fact that you have lone pairs on this central atom. So lone pairs are going to make your molecule not have symmetry, which is why lone pairs are going to make your molecule be a polar molecule. So this is probably before my time, but a student came up with this acronym, SNAP, and it stands for symmetry, nonpolar. So let's write that out. Symmetrical, nonpolar, asymmetrical, is polar. And so that may help you, right, be able to see whether the molecule has symmetry or not, whether it is polar or not.
This is a PhET simulation, and it does a really good job of showing you polarity. So right now, we have our two elements, atom A, atom B. So if I put the electronegativity at less for both of them, I have checked the bond dipole. There are no, I'm just going to go through and click everything. So there is no dipole arrow. They are equal. You can see there's more covalent bond character. What I like about this is we can show which one is more electrostatic, so which one has more negative versus more positive. We're smack dab in the middle. Electron density is equal. So let's take atom B. So if atom B moves towards middle, right? We now have that representation of that dipole arrow, and then we've got the slight positive charge on your atom A, slight negative charge on atom B, and you can see that the electron density has shifted towards atom B. We can also look at that atom B has more red to it, so therefore it has more of the negative charge, right? So then let's go with more. So if we have more, that dipole arrow got huge and those slight charges got a lot bigger. And then that electrostatic potential, the color, it's just a great representation, really went to the extremes. And you can see that it's more ionic behavior. And then when we look at electron density, it definitely pulls it a lot more towards that B side. Now what happens, I'm going to reset this, there we go. So what happens with multiple atoms, right? So we can move these wherever we want to move them. It doesn't really matter. All right, so I'm going to set these all down to less. So right now that they're all equal, so there are no dipole arrows. Atom B is going to go to the middle. So these black arrows are the bond dipoles. So that means the AB is a polar bond, CB is a polar bond. This orange arrow is representing a net dipole movement. So everything is going towards that B, which means that this molecule is going to be overall a polar molecule. And so then you can also see those slight charges. And then if we did more, you see how much bigger that net movement went. And we can just play with this, right? So if we have atom C has equal electronegativity to atom B, so that is a nonpolar bonds maybe, or it doesn't have any effect, but we still have that net arrow going in one direction. So if we have A and C being the more electronegative elements, right? So if they're like oxygen or something along those lines, they go down. And what's interesting is when you play with that bond angle, so here like CO2. So when we had CO2, I told you that those arrows canceled out. So because if these were both oxygens and carbon was in the middle, there is no molecular dipole moment. So where these atoms are positioned around the central atom is so important. So right now, because they are equal and opposite from each other, there is no net dipole moment. But as soon as we start to introduce angles, right, because that means now there's a lone electron pair here, as we had seen with our VSEPR chart, we now have a lone electron pair. We will have that net dipole movement in one direction. All right, so then looking at real molecules, right? So here we've got CH4 methane. So again, looking at our we have no molecular dipole because there is no difference. Looking at electron density, everything looks the same. There's really no different color change. But if we change to, let's do ammonia. So I'm going to take that away. So in ammonia, our arrows are all going towards nitrogen from those hydrogens, and we've got that net dipole moment going up from nitrogen away from those hydrogens, which means that nitrogen region is going to be a lot more negative and the hydrogen regions are going to be a lot more positive. And so the electron density has moved towards that nitrogen end and away from those hydrogen ends. So this is a really neat simulation to help you understand. If we have three different types of elements there, right? So oxygen is the most electronegative element on there. And we know the carbon hydrogen, those don't really have dipole arrows. So we have a net dipole going from the carbon up to that oxygen. So you can see the more negative side is oxygen, more positive side is the carbon hydrogen, and the electron density is towards that oxygen. So these are just really great visuals of trying to take this concept of polarity and what does it mean, and showing you on a model scale of what it is.
Okay, so this last slide, this excuse me, last document takes all of the information that we've learned about both ionic compounds and covalent or molecular compounds and puts it together. So if you follow this flow chart, this can help you figure out whether or not you're dealing with an ionic compound, what the difference in electronegativity would be, or whether or not you're dealing with a covalent compound, and then beyond that, whether or not you're dealing with a polar covalent compound with polar covalent bonds or a nonpolar molecule, nonpolar covalent bonds. So I definitely highly recommend that you have this out, kind of use this as a guide as you're doing your practice.